Hello, in this video we will be talking about synthetic division and zeros of a polynomial. Our polynomial can be written in this form, f of x equals g of x times q of x plus r of x, using the division algorithm, where g of x is called our divisor, q of x is our quotient, and r of x is our remainder. So if we look at this example here, we have a polynomial, f of x equals 2x squared minus 3x plus 4, and we have a binomial x plus 2. So we want to divide them. So first we do is we write 2x squared minus 3x on the inside, and then we have x plus 2 on the outside. So to do the division, we say how many x's can fit into 2x squared. So there would be 2 x's. So what we do first is we do 2x times the x right here, gives us 2x squared, but you also have to distribute that 2x into the 2. So 2x times 2 gets us 4x. And then what we do is we subtract them. So 2x squared minus 2x squared, that's 0. And then negative 3x minus 4x gives us a negative 7x. And then we bring down the 4. And the next step is, again, how many x's can fit into negative 7x's? That would be negative 7. So then you would multiply negative 7 times x, negative 7x, and also negative 7 times 2, and that gives us negative 14. Make sure you put parentheses and subtract. So negative 7x minus 7x, that's 0 again. And then 4 minus 14, that actually gets you a plus 14, which gives us an 18. So then we say, because this 18 is smaller than x plus 2, this is our remainder. So our function can be written in the form, you write the divisor first. The divisor is our binomial, x plus 2, times the quotient. The quotient is the result of our division. That's 2x minus 7, plus our remainder. Our remainder is just 18. And that right there is how you write your function in this form using the division algorithm. Now, a shorter way to divide polynomials is using synthetic division, which is a shortcut method of dividing polynomials in a particular case when the divisor is a first-degree polynomial of the form x minus k. So take this example from before. We have a polynomial, 2x squared minus 3x plus 4, and we want to divide it by the binomial x plus 2. So to write our synthetic division, first off is we identify what our k is. So because we have x plus 2, and we want it in the form x minus k, we think of it as x minus 2. So we can say that our k is negative 2. So when we do synthetic division, we write our k on the outside. Now what goes on the inside here is the coefficients of our polynomial. So we have 2x squared minus 3x plus 4, we have a 2, we have a negative 3, and we have a 4. To do the division, first thing is the first term, we bring it down below here. And then we multiply that 2 times our divisor. So 2 times negative 2 gives us negative 4. We put it right under the next coefficient, the negative 3. And then we combine them. So negative 3 minus 4 gives us negative 7. And then again, negative 7 multiplied by divisor. That's negative 7 times negative 2, which is positive 14. And then we add up the terms 4 and 14, gives us 18. And that right there is our remainder. So again, now that we've divided it, everything gets reduced down by a power. So for this first term here, 2x squared, it was before, now it's just 2x. And then we have a negative 7 before, that's the x spot, that's actually just negative 7, and we have our remainder. So this is right here is actually our quotient, our q of x part. And then this is our remainder, our r of x. So putting everything back together, just like before, we write out our divisor, so that's x plus 2, times our quotient, 2x minus 7, plus our remainder, which is 18. So just like before, this is our rewritten polynomial function. So let's look at the example right here. We have used syntactic division to perform the division. We have x to the 6 minus 3x to the 4th plus 2x cubed minus 6x squared minus 5x plus 3. And that's all divided by x plus 2. So when we're applying syntactic division to this, what you want to do is we need to find the term we need to divide with, which is our k term. So that k term is that term we're dividing by x plus 2. So if we round aside here, x plus 2 is like saying x minus negative 2. That negative 2 term is our k. So that's what we'll be using in our syntactic division. So we write our negative 2 on the outside. And on the inside of our division here is we write all the coefficients of our numerator here. So our numerator, we have coefficients for the x to the 6. We have 1. So there's no x to the 5th term. So we have to compensate it with a 0 for the x to the 5th term. For the x to the 4th, we have a negative 3. For the x cubed, we have 2. For the x squared, we have negative 6. For the x, we have negative 5. And then for the constant, we have a positive 3. So when we do syntactic division, first thing we do, bring the 1 down, multiply. Negative 2 times 1 is negative 2. Put it right under 0. 0 minus 2 is negative 2. Then we multiply again. Negative 2 times negative 2, positive 4. Negative 3 plus 4 gives us 1. Negative 2 times 1 is negative 2. 2 minus 2 is 0. And then 0 times negative 2 is 0. And then we have negative 6 plus 0 is negative 6. And negative 6 times negative 2 is a positive 12. Negative 5 plus 12 gives us 7. And 7 times negative 2 gives us negative 14. And finally, 3 minus 14 gives us negative 11. So that last term there, negative 11, is our remainder. So the result of this division here is that bottom part is our quotient. So it goes from x to the 6. Now our 1 here becomes x to the 5th. Before it was x to the 5th, now it's negative 2x to the 4th plus x cubed. Now notice there's a 0 here. So that 0 is the x squared term. So there is no x squared term. Move next to it. That's negative 6x. And then plus 7. Now, how do we represent a remainder? So how we write a remainder is we put the remainder, negative 11, over what we divided with, which is the x plus 2. So that's how you would write the answer after we use syntactic division. So now we talk about the remainder theorem. The remainder theorem states that if the polynomial f of x is divided by x minus k, then the remainder is actually just equal to f of k. So if we apply the remainder theorem, it will help us find the value of a function f of x at x equals to some k value. Let's look at it in practice. So we want to use the remainder theorem to find the value of f of 4 if f of x equals to negative x cubed plus 8x squared plus 63. So instead of having to plug that 4 into our polynomial here, we can apply the remainder theorem. So first thing is we need to identify that our 4 here is our k. So that's what we'll be using syntactic division with. So we write 4 on the outside. And our insides are coefficients. So we have a negative x cubed, so that's negative 1, 8x squared. But we're missing an x term, so just like before, we add a 0, and then 63 at the end. So go through the process of syntactic division, bring the negative 1 down. 4 times negative 1, negative 4. 8 minus 4 is 4. 4 times 4 is 16. And then 0 plus 16 is 16. 16 times 4 is actually 64. And then 63 plus 64 gives us 127. So that right there is our remainder. So by the remainder theorem, we can come to the conclusion that f of 4 is just equal to 127. And you can always verify that by taking 4 and plugging into the polynomial here, which will also get you the same result of 127. Now this example asks us to use synthetic division to decide whether k equals to -3/2 is a 0 of f of x equals 4x to the 4th plus x squared plus 17x plus 3. So to determine if k is a 0 of a function is when we apply synthetic division, our remainder should be 0. That will confirm that the k value is a 0 of the function. So first off is we apply synthetic division. So on our outside, we have the -3/2. That's what we're dividing by. That inside is the coefficient of our function here. But again, notice there is no x to the third term. So when we write on the inside of synthetic division, we have to consider that 0 in place of the x to the third term. So we have 4, 0, the x squared coefficient is 1, 17x is 17, and the constant is 3. So first thing first is we bring the 4 down. Now on the side here, let's actually do the multiplication here. -3/2 times 4/1. That will be -12/2, which gives us -6. So we put the -6 right under it, under the 0. Subtract 0 minus 6 gives us -6. And again, -3/2 times -6/1. That gives us 18/2, gives us 9. So 9 goes under the 1. Combine, 9 plus 1 is 10. Multiply again, -3/2 times 10/1 gives us -30/2, which is -15. Put it under there. And then finally, 17 minus 15 gives us 2. So -3/2 times 2/1 gives us -6/2, which is -3. Put it right under the +3, and 3 minus 3 gets us 0. So that's our remainder. So what does that tell us? That tells us that k equals to -3/2 is 0 of the function of f of x. And that will be our answer. This example asks us to show that x minus 2 and x plus 3 are factors of the function 2x to the 4th plus 7x cubed minus 4x squared minus 27x minus 18. So in order to determine if these binomials are factors, we have to remember that a factor of something essentially means that x minus k equals a 0, where k is our 0. So what we do is for the first one, the x minus 2, we set that equal to 0, and if we solve for x, we get 2. So that's our k. So we need to determine if this k is a 0 of the function. Just like the last example, we do that by using synthetic division, and if we get a remainder of 0, then yes, it would be considered a factor. So do synthetic division, our k value, and then we put our coefficients of the function. So we have 2, 7, -4, -27, and -18. So first term, bring the 2 down. 2 times 2 gets us 4. 7 plus 4 gives us 11. 11 times 2 is 22. 22 minus 4 gives us 18. 18 times 2 is 36. -27 plus 36 is a +9. And 9 times 2 gets us 18. So -18 plus 18 gives us 0. So that right there is our remainder, which is true, right? So we say that x minus 2 is a factor. So that's one answer. Now let's check for the other term, when x plus 3. So again, set x plus 3 equals 0. That tells us that x equals to -3. So we apply synthetic division again. this time with negative 3. Coefficients are still the same, 2, 7, negative 4, negative 27, and negative 18. Bring the 2 down. Negative 3 times 2 is negative 6. 7 minus 6 gives us 1. 1 times negative 3 is negative 3. Negative 4 minus 3 is a negative 7. Negative 7 times negative 3 gives us a positive 21. And then negative 27 plus 21 gives us a negative 6. And then finally, negative 6 times negative 3 gives us positive 18. And negative 18 plus 18 gives us 0. So the remainder, again, is 0. So x plus 3 is also a factor. And so both terms, both binomials, x minus 2 and x plus 3, are both factors of our function here. The rational zero theorem is a method to determine the possible rational zeros of a polynomial. The method is as follows. List all factors of the constant coefficient. These will be the possible values that p can take. List all factors of the leading coefficient. These are the possible values that q can take. Determine all possible values of p over q. Make sure to include both positive and negative possibilities. And then use synthetic division together with the remainder theorem. Determine if p over q is a zero of the polynomial function. Let's look at an example. Find all possible rational numbers p over q of the polynomial f of x equals 2x to the fourth plus 7x cubed minus 4x squared minus 27x minus 18, and find at least one zero. So the first thing we need to do is we need to figure out what our p and our q is. Our p is always our constant, which is in this case that negative 18, and our q is the leading coefficient, which is 2. So first thing we do is find all possible factors of p, which is 18. So that would be plus or minus 1, 2, 3, 6, 9, and 18. And all possible factors of q, which is 2, would just be 1 and 2. But now we want, using the rational zero theorem, we actually want p over q. So how this works is you take every possible p, you put it over every possible q. So our q is only, good thing is our q is only two numbers, 1 and 2. So you would have every p over 1, which would be the original p's again, because it'd be 2 over 1, 1 over 1, 3 over 1, so on. And then now we take the next one is when we take every p, we put it over 2. So 1 over 2 gets us 1/2. 2 over 2 gets us 1, which we already have. Don't have to write it again. 3 over 2 gets us 3/2. 6 over 2 is 3, which we already have. 9 over 2 would be 9/2. And then finally 18 over 2, which gives us 9 again, which we already have. So we would stop there. So these are our possible rational zeros, the p over q factors that we just found. Those are our possible rational zeros. Now we need to find at least one zero. So what we do is you pick one of the possible rational zeros and you test it using synthetic division. After you test it, if you get a remainder of 0, then that possible rational zero is a rational zero. So let's say we test with the possible rational zero of 2. So what goes on the inside is our coefficients here. So we have 2, 7, negative 4, negative 27, and negative 18. So first term, we bring the 2 down. 2 times 2 gives us 4. 7 plus 4 gives us 11. 11 times 2 is 22. Negative 4 plus 22 is 18. 18 times 2 is 36. And then negative 27 plus 36 is positive 9. And finally 9 times 2 gives us 18. And we see negative 18 plus 18 is 0. So that's our remainder. So what does that tell us? That tells us that 2 is a 0 of the function f of x. And that would be our answer here. You can determine the number of zeros of a polynomial by its degree. A polynomial of degree n has at most n distinct zeros. A polynomial may have factors that repeat more than once. The number of times a factor, and hence the corresponding zero, repeats is referred to as the multiplicity of the zero. Non-repeating zeros are said to have multiplicity of 1. For this example, we're trying to find all zeros with a polynomial function f of x equals x times x squared minus 4 times x plus 5 quantity squared. So when you want to solve for a polynomial function, the function should be in factored form, which it is in this case. So all we have to do now is set these factors all separately equal to 0. So x equals 0, x squared minus 4 equals 0, and x plus 5 quantity squared equal to 0. So let's now solve each factor separately, solve for x. So for the first one, x equals 0 is already solved. We just leave it alone. For this one, we add 4 over, x squared equals to 4, and then we take a square root both sides. So x equals 2 plus or minus 2. Now x plus 5 squared equals 0. There's two ways we can approach this. We can take a square root like we just did. So it gives us x plus 5 equals 0, and move 5 over to the right side, gets you negative 5. Or alternatively, you can think of this as x plus 5 times x plus 5. And if you solve them, because they're the same term, you can just focus on one of them and set that equals 0. Gets us negative 5 as well. But this is where the multiplicities come in. Because this is x plus 5 quantity squared, it basically tells us that the 0 x equals negative 5 happens twice. So the multiplicity would be 2. As opposed to these two zeros, multiplicity does x equals 0 is just 1. And then the plus or minus 2, because they're two separate zeros, positive 2 and negative 2. This is just both multiplicity of 1 as well. So the number of zeros here actually does match up with our polynomial function, because our polynomial function has a highest degree of actually 5, because you have an x squared that gives us x cubed, and another x squared gets us x to the 5th. So if we were to FOIL or distribute everything out on this polynomial, we would get the highest degree to be x to the 5, which also tells us that there are 5 total zeros, because we have 1 0 for x equals 0, that's 1. We have 2 negative 2, that's 3. But we also have x equals negative 5 with a multiplicity of 2. That gives us a total of 5 zeros. So there's a total of 5 zeros here. And that would be our answer. So now let's think about when we're actually given the zeros of a polynomial function and we need to find that polynomial function. So this question says, find a polynomial function whose zeros are 1 and 2, multiplicity 2, for which f of negative 1 equals to 6. So right off the bat, let's list what our zeros are. So our zeros are given to us are 1, so we can say this is x equals to 1, and then 2, however, it says is a multiplicity 2. Multiplicity 2 basically means that we have x equals 2 twice, 2 times. So when we want to write our polynomial function, we're essentially kind of working backwards. So if you think about previous examples, before we were to solve for x, we got in the form basically, if we move these terms back over to the left side here, we would basically have x minus 1 times x minus 2. However, because it's a multiplicity 2, there's 2 of them. Instead of writing x minus 2 times x minus 2, we can represent as x minus 2 squared. And that's equal to our function, f of x. However, there could be a coefficient in front that we're not too sure what it is. So we would call that coefficient a here, some arbitrary coefficient. Now, we need to actually solve for a to make sure that there's nothing there, or there's no term there. So how do we figure it out? What we do is we use the fact that f of negative 1 is equal to 6. So what that basically means is that when x is equal to negative 1, our f of x, or our y, would be equal to 6. So applying this, apply f of negative 1 equals to 6. So we replace x with negative 1 and y with 6, which would help us solve for our a term here. So we would have 6 equals to a times negative 1 minus 1 times negative 1 minus 2 squared. Okay, so if we evaluate the right side, on the first parentheses, negative 1 minus 1 gives us negative 2. And then negative 1 minus 2 is negative 3, but we're squaring that, so that should give us a positive 9. Now if we multiply, negative 2 times 9 gives us a negative 18, so we can write this as negative 18a is equal to 6. To solve for a, we divide both sides by negative 18. So a is equal to negative 6 over 18, but that can actually be reduced, because if we divide by 6 top and bottom, gives us negative 1 over 3. So our function here, polynomial function here, can be represented as negative 1/3 times x minus 1 times x minus 2 quantity squared. And that right there would be our answer. Now let's look at an example involving complex zeros. So the question says, find all zeros of the polynomial function f of x equals x cubed minus 7x squared plus 17x minus 15, given that 2 minus I is a 0. So one thing to consider is that whenever we have given a complex zero, we also have to consider its complex conjugate as a 0 as well. So remember that a complex number can be written in a plus or minus bi. So if we are given a plus bi, we should also be given its conjugate. We know it has also its conjugate as a 0, a minus bi. So we know that one of our zeros is going to be 2 minus I. Then its complex conjugate, x equals 2 plus I, is also a 0. So now what we do is to find the other zeros, we have to use syntactic division. So using the first 0 that's given to us, 2 minus I, we divide that, and then we write out the coefficients of our polynomial function. So we have 1, negative 7, positive 17, and negative 15. So now we start doing the syntactic division process. First things first is we bring the 1 down. Now we multiply. Now we multiply 1 times both terms, 2 and negative I. So 1 times 2 gives us 2, and then negative I times 1 is negative I. Now we combine. So when we add this, we're only adding the negative 7 to the real part of our complex number. So we would have negative 7 plus 2 gives us negative 5 minus I. So now when we multiply this, let's write on the side here. We're multiplying 2 minus I times negative 5 minus I. So when we multiply, we're doing the foiling process. So 2 times negative 5 gives us negative 10. 2 times negative I is negative 2I. Negative I times negative 5, positive 5I. Negative I times negative I gives us positive I squared. Now, we know we can combine like terms, so we have negative 10. Negative 2 plus 5I is positive 3I. But remember, I squared is actually equal to negative 1 because I is equal to square root negative 1. So we can actually turn this into a minus 1 which then we can combine, which becomes negative 11 plus 3i. So that result will go under our 17 here. Okay, so then now we combine 17 minus 11 gives us 6 plus 3i. And again, we do the foiling process again. So let's write on the side here. 2 minus I. We're multiplying with 6 plus 3i. So we FOIL once again. 2 times 6 is 12. 2 times 3i is 6i. Negative I times 6 is negative 6i. And negative I times 3i is negative 3i squared. But we see that when we combine, the 6i and negative I become 0. So we have 12. And then negative I squared is negative 1 times negative 3 gives us a positive 3. Which if we add, we get 15. So we put that right under negative 15. And obviously if we add them, we get the remainder 0. Which is true because 2 minus I is a 0. So now that we reduced it by a power, so right now we still have a lot of complex coefficients. However, because we know that 2 plus I is also a 0, we can go straight into doing another synthetic division with the given 0 of 2 plus I. So let's do it again. Bring the 1 down. So 2 plus I times 1 gives us 2 plus I. Now if we add, this time we have an I, so we're going to be adding the i's as well. So negative 5 plus 2 gives us negative 3. And negative I plus I gets us 0. So we're left with just the real part, which is negative 3. And then again, we multiply negative 3 times 2 plus I. So negative 3 times 2 gives us negative 6. And negative 3 times I gives us negative 3i. Again, if we combine terms here, we actually get 0, which is remainder, which again is true because 2 plus I is a 0. Now all that's been said, what happens is the first time we did synthetic division, the leading term went down to x squared. So then if we did a synthetic division again, the leading term now is just x. And the term next to it before it was x squared, then we did one synthetic division becomes x. If we do another synthetic division, that negative 3 is just a constant negative 3. So now that we have that, this is what boils down after we were to do synthetic division twice. And to find the remaining 0, because our leading term here is x to the third. That means that we know there's going to be 3 zeros. We know that 2 minus I and 2 plus I are already our zeros. So the last term after we divide them out, we're left with x minus 3. We set that equals 0. Solve for x. Gives us 3. So that tells us that our zeros are going to be the two given complex, 2 minus I, its complex conjugate 2 plus I, and the last real 0. The last 0 is a real number, which is just 3. So that right there is our zeros of the polynomial function. Alright, so let's look at another example involving complex zeros. We're trying to find a polynomial function f of x of least degree having the zeros of 1 and 2 plus 3i. So as stated before, because we have a complex 0, we also know its complex conjugate is also 0. So the third 0 in this case here would actually be the conjugate of 2 plus 3i, which is 2 minus 3i. So now that we have our 3 zeros, we need to, like before, work backwards to get our polynomial function. So how we do that is we first off, let's say we let these zeros be x equals 1, because essentially when we solve for x for our polynomial function here, we're gonna get x equals 1, x equals 2 plus 3i, and x equals to 2 minus 3i. So now we can write this function, this polynomial function, as some a constant, a coefficient, times. Now our first 0, x equals 1, can be moved over to the left. We have x minus 1. The next one is, again, we're moving it over, but this time make sure you're moving over both the real part and the I part of the complex number. So we have -2 and -3i. And lastly, for our final complex 0, 2 minus 3i, we move it over. We have x minus 2 plus 3i. So in this case, because we're not given any other x or y value, we can assume that our a is going to be 1. So we can simply write this as x minus 1, x minus 2 minus 3i, and x minus 2 plus 3i. So this is our polynomial function in the factor form. And of course, if required, we can always expand this by the process of foiling or multiplication. Sometimes it will be beneficial to predict the number of real, positive, and negative zeros of a polynomial. So the French mathematician René Descartes did such a thing with his rule of signs. So the rule of signs will help you determine how many real zeros there are in a polynomial. So the number of positive real zeros is equal to the number of variations in sign occurring in the coefficients of f of x, or less than this number by an even integer. So i.e. by 2 or 4. So essentially, you would look at your polynomial function and look at how many sign changes there are. The number of sign changes will be the number of possible positive real zeros, or the number of sign changes less than that number by an even integer. Now the same thing can be said with to find negative real zeros, but the difference is that you would apply it to f of negative x. So you do f of negative x, count the number of sign changes, that will be the number of negative real zeros, or whatever that number is, subtracted by an even integer, and that will be Descartes' rule of signs to help determine the number of real zeros you have in a polynomial. So now let's apply Descartes' rule of sign to an example. So the question says we determine the different possibilities for the number of positive, negative, or complex zeros for f of x equals to 5 of the x to the 6 minus 6x to the 5th plus 7x to the 3rd minus 4x squared plus x plus 2. The first thing we do is we want to think about the number of positive zeros. So to determine the number of positive zeros, what we do is we count the sign variations between each term in our original function here. So if we look at our leading term here, it's a positive 5. So to go from positive to negative, that's one sign change. From negative 6x to the 5th to positive 7x to the 3rd, that's another sign change. From positive 7x to the 3rd to negative 4x to the 2nd, it's another sign change. And finally, negative 4x to the 2nd to positive x is another sign change. Because now, between x and 2, they're both positive, so there would not be a sign change. So the number of positive zeros would be 4, because that's the number of sign changes that we saw, or the number of sign changes subtracted by the smallest even number. So if we have 4 already, the one smaller than that would have to be 2. So 4 minus 2 gives us 2. So that is a positive number of positive zeros, number of possibilities for them. Now for negative zeros, we have to determine, first off, we have to consider f of negative x, which means everywhere we have an x in our function, we substitute it with negative x. So it would look like 5 to negative x times negative x to the 6 minus 6 times negative x to the 5th plus 7 times negative x to the 3rd minus 4 times negative x to the 2nd plus negative x plus 2. So if we were to simplify this, we have negative x to the 6th power. So every time you have an even power, it makes the inside become positive. So we have just 5x to the 6. When you have an odd power, that keeps it negative if it were negative. So negative x to the 5th stays as negative x to the 5th, but there's a negative 6 in front. So it becomes positive 6x to the 5th. Negative x to the 3rd becomes negative 7x to the 3rd. Negative x to the 2nd becomes positive, but there's a negative in front, so negative 4x to the 2nd. And this becomes plus minus x becomes just negative x. And we have plus 2. So now let's count our variations. So between 5x to the 6th to 6x to the 5th, no sign change. But from 6x to the fifth to negative 7x to the third, there is a sign change. From negative 7x to the third to negative 4x squared, no sign change. From negative 4x squared to negative x, no sign change. But from negative x to 2, there is a sign change. So the number of possible negative zeros would be the number of sign changes, which is 2, or we take that 2, subtract by the less even number, so 2 minus 2 in this case would be 0. So our possibilities would be either 4 for positive zeros, it would be 4 or 2 possible ones. And then for negative zeros, it would be 2 or 0. And that would be our different possibilities.